What causes lightning? Lightning can be a beautiful and scary part of Earth's weather. You probably have seen lightning in a thunderstorm, but do you know why lightning happens? Lightning comes from electrical charges that build up within a storm cloud. Thunderstorms form when warm, moist air rises high into the atmosphere. This rising air is called an updraft. As air rises in the atmosphere, clouds form when water vapor in the air cools into water drops, called cloud droplets. Some cloud droplets freeze into ice crystals. These cloud droplets and ice crystals collide and form larger particles called graupel. As the ice crystals rise up, they collide with the larger and heavier graupel. These collisions result in positively and negatively charged particles. Ice crystals are small and light. The updraft carries the positively charged ice crystals higher and higher into the cloud. The thunderstorm cloud is mostly negatively charged, which causes a mostly positive charge to form on the ground. When these opposite charges become strong enough, there is an electrical discharge, an energy release, in the form of lightning. Lightning often connects the negative charges in the cloud to positive charges on the ground. This is called cloud-to-ground lightning. Why does lightning often hit trees, telephone poles, or other tall structures first? Trees and telephone poles are often the tallest objects on the ground. So, they are closest to the storm cloud and the first thing in the path of lightning. Lightning can also stay within a cloud or even travel between two clouds. This happens when lightning travels from a negative charge in one cloud to a positive charge within another cloud. This is known as intra-cloud lightning. By the time you see lightning in the sky, a storm is probably already underway in your neighborhood. But tracking lightning from space can help meteorologists predict the intensity of a storm. NOAA's GOES-R series weather satellites captured this imagery of lightning during a series of thunderstorms over the Midwestern United States. Imagery and information from these satellites help forecasters to predict the intensity of a storm and whether or not the storm will produce high winds or tornadoes. Find out more about Earth's weather at NOAA SciJinx.
Satellite, you're thinking something the size of a car or bigger. It's the size of a loaf of bread, and that's our satellite. There's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. There's been evidence, and others have seen this, but again, there's never been a satellite dedicated looking down at Earth for these terrestrial gamma ray bursts.
We want to make artificial signals similar to lightning and see what the board does, make sure it's filtering those signals the way we want.
We're going to put it into HDL code and then get it through this chip.
One of the tenets of the CubeSat program is to involve undergraduate students at all levels, from design to building to some of the theory, data acquisition, every aspect of this. So we're really training here the next generation of space scientists, of satellite engineers. As soon as the launch goes up and they know they're a part of that satellite and data's coming in, I mean, that'll be with them throughout their life.
Storm collisions among rain and snow cause different parts of the cloud to develop positive and negative electrical charges. When the strength of the electric field overcomes the insulating properties of air in the thundercloud, a lightning flash occurs. Most lightning occurs entirely within the cloud and is called an intra-cloud flash.
The source was a thunderstorm just 3,000 miles away. Earth's magnetic field seems to have corralled about 100 trillion positrons from the storm into a tight beam and funneled them all the way to the spacecraft, explains lightning expert Joseph Dwyer of the Florida Institute of Technology. Something was producing antimatter above the clouds of Earth and hurling it into space at nearly the speed of light. But what? Dwyer and collaborators at the NASA Marshall Space Flight Center and the University of Alabama believe they have figured it out. The answer, says Dwyer, is dark lightning. Dark lightning may sound like an oxymoron, but there is growing evidence that it is real. Ordinary lightning happens when electric fields build up inside thunderclouds. Electrons rush from one part of the cloud to another to try to cancel out the growing voltage. The flash of light we see traces the path of the charged particles, which heat the air 5 times hotter than the sun. If Dwyer's ideas are correct, dark lightning is a competitor of ordinary lightning. It also tries to cancel out the thunderstorm's electric fields. The process, he says, goes something like this. Under the right conditions, electric fields in a thunderstorm can create a powerful avalanche of electrons, shooting upwards nearly as fast as light. The electrons collide with air molecules, in turn producing gamma rays. Earth-orbiting spacecraft have been observing gamma ray flashes from thunderstorms since at least the mid-1990s. Next, the gamma ray energy transforms into a pair of particles, an electron and a positron. Successive collisions between these particles and other air molecules create a new batch of positrons and electrons, and the cycle repeats. A continuous feedback loop forms, like nuclear fission. It's a natural, self-generated, self-sustained particle accelerator, says Dwyer. Once the feedback loop gets started, he says, it can discharge parts of a thundercloud as fast as lightning. And, because the cascading electrons and positrons generate more gamma rays than visible light, the whole process is practically invisible to the human eye. Researchers once thought that gamma ray flashes from thunderstorms were a weird byproduct of ordinary lightning. Now they are thinking it is a sign of dark lightning instead.